Hello, and welcome to Logarithmic Functions. These are the applications. Oh, and my name's still Tuesday. All right, so exponential decay and half-life. Here we have a graph of decay of carbon-14. It's got quite the half-life here. An exponential decay function has the form q of t equals q subscript 0, so q sub 0, e to the negative kt, where q sub 0 and k are both positive. E is the Euler number e, and t is a variable. Q sub 0 and k will actually be numbers. All right, so this formula has a negative sign in it. Q sub 0 represents the value of q at time t equals 0. Some people call this q naught, q initial, q0, q sub 0. There's many different ways that people might refer to it, but that's always what it means. It's the initial value of q. It's the value of the q at time 0. And k is called the decay constant, and the decay constant is related to our half-life. Half-life is the amount of time that it takes for half the substance to decay. So I think that's around here. Where are we? 50. So 5,700 years, I think, is around the half-life for the decay of carbon-14. We can see if we have 100 grams, we have about 50 grams around 5,700 years. So that's what half-life means. We also have exponential growth and doubling time. An exponential growth function has a very similar form. The only difference is it's missing a negative sign. So if you have a negative in the exponent, it's a decay. If you have a positive in the exponent or no sign showing, assumed to be positive, you're going to have a growth function. Q sub 0 is still the value of q at time t, always will be in math, and k this time is called the growth constant because we have a growth formula, it's a growth constant. And instead of half-life with growth, we'll have a doubling time. So if we start down here at, oh my goodness, it's hard when we have 0. But how long does it take for this to double, to go from, if I could see my units better over here, from 10 to 20. So here's from 10, double it to 20. It looks like it's about 3 years. That looks like days. It's days. Oh, look, it says right there, a doubling rate of 12.4 days. I can read. It's fundamental. All right, so let's look at an example. A couple of quick examples. Write an appropriate exponential function for the given information. If we know that the quantity is 75, so maybe there's 75 bacteria when time is 0, and they double in 4 units of time, we know that our q sub 0 is 75 because that's the value of q when the time is 0. That's exactly what that notation means. Our k value is always natural log of 2 divided by the doubling time. Natural log of 2 over 4, and if you want, you could pull out a calculator, but why? Unless you actually need to know the decimals, this is a fine equation, 75e to the power of natural log of 2 divided by 4 to the t. Right? Positive exponent, it's doubling. We found our k value. We found our q sub 0. Let's do it again. Q equals 1200 when t equals 0. That tells us that q sub 0 is 1200. Our half-life is 249. So just like doubling time, the formula for k is the same. What changes is the exponent. And you can see here that I have the wrong exponent. Isn't it amazing what you could find by reading over your work? This should be a negative kt because it's a decay equation. Decay equations will always have a negative exponent. We say our decay constant is a positive value, so we have to remember to put in the negative sign, and I failed you. But we all make mistakes, and the goal is not to erase them, pretend they didn't happen. It's to learn from them, and I need to learn to pay attention. All right, let's look at continuous compounding. We want to find how long to the nearest year it will take an investment to triple if it's continuously compounded at 7.2% per year. So let's identify our values. All right, how much are we investing? We have no idea, right? Some investment. So let's call that P. We'll just call it P for our principal. Our interest rate is 7.2%. 7.2 divided by 100, which is 0.072. Here's how I think of it. We know how to write 7 cents, right? 7%, 7 cents. And then the 2 follows. That works for me. We have no idea what the time is. That's what we're trying to find. So we have time as a variable. And A is the triple, right? Whatever I invested, P dollars, my future amount is triple that. All right. So let's substitute. A equals PE to the R times T. We only have one set of numbers in here, and that's for our interest rate R. But we can still solve this. Let's take this equation to the top of the next page. The first thing we want to do is divide both sides by P. If we divide both sides by P, we can isolate our exponential. We always want to isolate whatever it is we're working on. Isolate a square, isolate an exponential, isolate a logarithm, isolate whatever it is you're working with. So we divide both sides by P and we realize it doesn't matter what we invest, right? It doesn't matter. It happens to triple. Once we have this exponential isolated, we can convert to logarithmic form. 0.072t is the power. So 0.072t will equal a logarithm. The base of the logarithm is e, so I'll use the special notation. That's our special natural log. It's an L, not an I. The natural log of 3 is equal to the exponent. We can isolate t now by dividing both sides by 0.072. And we get 15.258 for our t value once we evaluate it in a calculator. Remember, this problem started with words. Let's finish it up with words. It will take a little over 15 years for this account to triple in value. So if you put in $1, it'll take 15 years to get 3. But if you put in $1 million in 15 years, you'll have $3 million. It's all in where you start. All right, thank you very much for watching. I hope you're having a fabulous day. Smile at someone just because.